Good morning. Today is December 8th, 2018, and this is the John Chappell Natural Philosophy Society Science Chat, and I am your host, Franklin Hu. And we encourage you to support our mission at naturalphilosophy.org, where you can join us or renew your membership. We are also can be found on social media in Facebook, as well as on YouTube. Now, I just recently updated the link in the announcement, so it points at that YouTube channel, since it was previously pointing to an older link that didn't have all the videos. But I am trying to post all the videos relatively soon after. And if you'd like to help us, we encourage you to join our base camp at hq.naturalphilosophy.org. And the rules of conduct for this meeting is to treat everyone with respect. I'd also ask that if you're not speaking, please mute your microphone. And if you're not speaking, please also turn off your camera. But if you do speak, I would encourage you to turn on your camera at that time. And then we have our upcoming conference, June 26th to 29th at the University of Washington in Seattle, featuring Dr. Gerald Pollack. So last week we had discussed the electromagnetic wave. Ian had brought up his paper showing that the electromagnetic wave acts very much like a sound wave, at least from an equation kind of standpoint. They seem very similar, more similar than different. So this week I decided to take that theme one step further and just look at the hypothesis that the electromagnetic wave really is just like an ordinary sound wave, which is a compression wave in a medium, and just see how far that gets. So I wrote an entirely new 3-page paper for that. And so for this meeting, I'll first go through this paper. Now, if you have questions, can you please put those in the group chat? And if I see them, I'll get to them. But first, please let me get through the paper as just a regular presentation, since there have been some complaints that there have been so many questions during the middle of presentations that it was kind of hard to keep track of what's going on. So please put your questions in the group chat. Like I said, if I can inline get to them, then I'll do that. Or otherwise, hold your questions to the end, and then we can start our discussions then. So this is my new paper, hot off the presses, just finished it last night, which proposes the electromagnetic wave as just being exactly the same thing as an ordinary sound wave. So I start off this paper by asking the question, what's wrong with this picture? So here we have the standard mainstream description of what we think an electromagnetic wave is. And in the picture you can see there's some red lines, and that represents time-varying magnetic field. And then we see the blue lines, which is a time-varying electric field. And what this picture is supposed to be meaning is that we see this electric field which rises in intensity. You get the electric field rising in intensity, heading in that direction. I mean, I suppose, you know, if there were charges present, there would be a plus charge here and a minus charge here, and well, I don't know. This is kind of hard to understand, but the field strength is increasing, decreasing, and then we have a magnetic field here, which is also increasing, decreasing. You know, that would be like what you might observe between a north and a south pole, except somehow it's increasing and decreasing. And this is based upon the equations of Maxwell, which predict that a time-varying electric field is associated with a time-varying magnetic field. Now, I would claim that this conception is purely theoretical and really only exists on blackboard equations. And nowhere has anyone shown experimentally that these rising electric and magnetic fields actually exist in a traveling radio or light wave. And I think fundamentally we are quite capable of measuring that. I mean, if I put a magnetic detector as this wave travels by here, I should be able to easily measure rising and falling magnetic field. But as far as I know, we've never, ever really done that. So it's kind of curious. We believe in something which is, like I said, basically completely theoretical, but never backed it up with an actual experiment showing that this is actually what happens. The other main problem with this picture is that mainstream fundamentally doesn't even know what an electric or a magnetic field physically really is. We just know that they exist. We know how to measure these things, but we don't know what they are, say, classically, or how they propagate. Or really, we can't say much about what those things are. So that, I believe, is just a really very big problem. I mean, fundamentally, you know, most of the time, magnetic and electric fields must be created in the presence of real charges. So in the case of magnetic fields, you must have charges in motions, like some kind of electron in motion. And in order to have an actual electric field, you need to have a charge present, like, say, an electron or a proton. Something has to have a charge to emit the field. But in the case of the electromagnetic wave, we are to believe that we have this self-propagating electric field. And this, if you notice, this electric field and this magnetic field rise and fall at exactly the same time. They go to a maximum, and then they completely die out to zero. And then somehow magically, after it's dead and it's zero, it magically resurrects itself, goes to a maximum, and then goes back to zero again, which just seems extremely unlikely how it could do that. So we discussed a bit about, you know, the derivation of the electromagnetic wave and how that didn't really make any sense. But I realized that, you know, anyone else watching this will probably say, hey, there's like, you know, several hundred years worth of evidence to support this, and every experiment agrees with this, and everyone thinks that this is exactly the way it works. And so, yeah, so there may be some other evidence, and maybe I'm just being a bit naive, but I'm not going to try and address, you know, all of that, all the possible evidence there is in favor of this picture. Rather, I'm just going to basically start fresh. If I were to look at this without any knowledge of any previous knowledge of how people think the electromagnetic wave works. So going back to basics, we think that light and radio waves are a wave phenomenon because they appear to obey basically all the same laws as sound waves. And for example, Ian's paper last week basically showed that that was fairly true, that there aren't any other anomalies in the electromagnetic wave which would indicate that it doesn't follow the laws of sound. And for example, the ability to form an interference pattern is another strong piece of evidence that what we're dealing with is a wave, because waves have the ability to cancel and to reinforce. And we see that in the generation of interference patterns. And specifically, EM waves have a measurable frequency and a wavelength, but probably an amplitude and a wavelength. It's two separate things which we can physically measure. They obey the same kind of things like Doppler formulas for approaching and receding sound wave. And really, most every experiment you could come up with, except for very few exceptions, show that light waves behave exactly the same as sound waves. But instead of thinking that the electromagnetic, just a moment. But instead of thinking that the electromagnetic wave is exactly like a sound wave, we instead think of it as this extremely complex blend of electric and magnetic fields. So, but I would say that this is wrong. As much as everyone thinks it's right, I'm going to go against the crowd and say that that is, in fact, completely wrong. And go back to the old hypothesis that the EM wave is exactly the same thing in nature as a sound wave. And that means that the EM wave travels as a simple compression wave in a particulate medium. So we think we completely understand how a sound wave travels. And so it would be the advantage that if we can think of it as exactly the same thing as how sound travels, then I think we could say we would know exactly how an electromagnetic wave travels. And really the only thing that is happening when a wave travels through space, like a light wave, is that there's a medium that's being alternately compressed and rarefied, and nothing more than that. People try and make this more complicated, but I'm just putting up this hypothesis that an electromagnetic wave is nothing more than a compression and rarefication of a medium, of an elastic medium, which is exactly the same as what we think sound is. For example, it would be ridiculous to say that a sound wave is traveling with an electric and magnetic component. And it would be inconceivable that these two components can somehow travel at a 90-degree angle to each other. You know, it just makes no conceivable sense that I gotta change my thing here. Makes no conceivable sense that we could possibly describe a sound wave in the same manner that we describe electromagnetic waves. So the other thing is that you know, in spite of the name electromagnetic wave, you know, I don't think that the EM wave actually has anything to do with the magnetic or electric field. Those things exist, but just like that doesn't have anything to do with sound traveling through air, I don't think that has anything to do with the electromagnetic wave traveling through space. So, as I said, you know, if it did have anything to do with the electric and magnetic fields, I think we would have been able to trivially measure them, but we can't. And if you try and produce an electromagnetic wave by, say, using a time-varying electric field, that doesn't produce a long propagating electromagnetic wave. Similarly, if you try and produce a time-varying oscillating magnetic field, that doesn't create a long propagating EM wave either that can travel long distances. These things were tried in the early days of radio, and it just doesn't work. For example, if you do this with the magnetic waves, you can in fact create a magnetic wave. It doesn't travel very far, and you can recover the energy. This is how you can wirelessly transmit significant amounts of power through the air by using a time-varying magnetic field. But you don't get like a radio wave out of these things. So you would think that if the electromagnetic field were really this time-varying electric magnetic thing, you'd think we'd be able to generate them with time-varying magnetic and electric fields, but that just doesn't work. So that's yet another piece of evidence that these electromagnetic fields don't have anything to do with the propagation of things that we recognize as a light wave. So I would think that if the electromagnetic wave is in fact a wave, then the only thing it can be is a compression wave in a particulate medium, just like sound. So none of this transverse wave stuff, none of this time-varying electric field stuff, none of this magnetic field stuff. All it is a simple compression wave. So what are the problems with this idea? So since pretty much most of the experiments agree that the EM wave is a simple compression wave like sound, then what are the problems that prevent us from adopting this simple conception? Now, the first obvious problem is figuring out what this medium is. And so for a sound wave, we have air molecules, and we understand that very well. But what does the EM wave travel through? We find that EM waves travel through perfect vacuums, which don't look like they contain anything at all. So how can an EM wave be like a sound wave if there isn't any particulate medium to travel through? So that would seem to be a problem. I mean, if this is a problem, it makes people think that light is actually, quote unquote, a photon, which is literally like a matter particle. So if you have a matter particle, that can travel through absolutely empty space, no problem. It doesn't need a medium, but then it wouldn't be a wave. But what I'm talking about is that that light, as it travels, is actually traveling as a wave, like sound. And that really requires a physical medium. Now, this isn't actually such a crazy idea, in that in the past, prior to Einstein, it was actually commonly accepted that there was this invisible medium that people would refer to as the ether, and it was commonly thought that EM waves were really just like a sound wave, since the vast majority of experiments conducted up to that time agreed with that hypothesis. So this isn't some crazy crackpot idea. A lot of people used to think that's actually how it worked. But the question still remains about, what is the ether and why haven't we detected it? I mean, that's a pretty big problem. If we say there's some material ether out there, but no one's been able to detect it, well, it's easy to see why people wouldn't believe you. So, but fundamentally, if we were to claim that the EM wave is a sound wave, then it needs to be made out of tangible matter, like oxygen and nitrogen molecules, that can be compressed. But we don't see any tangible matter in a vacuum, so this is a paradox. But no matter what it is, in practice, any particulate physical medium would do the trick. So I'm going to propose a particular possibility candidate for what this ether is. So to fit the bill of a medium for the EM wave, it has to be made out of ordinary matter, nothing exotic. It has to be made of things that we currently recognize, but yet be completely undetectable. Now, once Dirac once thought that there might be a sea of electrons. Oh, yeah, I just heard all that coughing. You might want to mute yourself. But I think, for example, the charge would easily give that away. So we would want something that really doesn't have a charge, should be neutrally charged. So the simplest particle that we know about, which is neutrally charged, would be the neutron. So Suppose we run with that. So we fill all of space with a sea of neutrons. Since neutrons have no charge, they interact very, very little with ordinary matter. Neutrons, if you didn't know, can easily pass through a great deal of matter without being stopped. I mean, I could shoot a beam of neutrons at you. They would go through you, through your house, and through your neighbor's house. They interact very little with matter. I think you actually have to have several feet of lead to actually even slow them down. So the question is, if we were surrounded by a sea of neutrons, would we necessarily know it? I would contend I don't think so, because the interaction with ordinary matter would be so little that, if you had a jar filled with neutrons, it would in fact look like a jar with a complete vacuum. There would be no practical way to create a material that could physically hold neutrons in a container. As I said, they flow through everything, much like water through a net. So any container that you could possibly build would likely have exactly the same pressure on both sides of the barrier. And we could therefore not detect any pressure differences like we would if there were air molecules in the container. I would contend that a sea of neutrons would be very, very, almost impossibly hard to detect. And there are other reasons to think that what we consider a vacuum is really completely full of material particles. And if you listen to the mainstream, they would often refer to things as virtual particles and quantum foams. But all of these things really point to a material substance existing in what we call a vacuum. Now, there are also other significant experiments, such as the Lamb shift experiment, which basically say that the only way that they can figure out this shift happening is if space were just filled with the sea of positrons and electrons. So I would take this one step further and contend that the neutron is really a combined positron-electron dipole particle. And I have dubbed this particle the poselectron to separate it from what we normally call a neutron, which is something which is typically found in the bound atomic nucleus. So I believe it takes on a different physical characteristic as a poselectron. So, and I would contend that this poselectron would be a completely stable, neutrally charged, ordinary matter particle. It would have a measurable mass to it, being composed of a positron and an electron. So I would propose that this precisely defines the nature of the neutron in terms of ordinary particles, matter particles, nothing exotic, which we currently think of as fundamental, which is just the electron and the positron. I mean, so far, that's the only easily found particle for which we cannot find any evidence of it being composed of anything. So far, most of the experiments would say that that is fundamental. So this solves one of the major problems with the EM wave by defining the particulate medium that is both made out of ordinary matter particles, but it is generally completely invisible. So that solves the big problem of, if it's a wave, then what is it waving in? So it's waving in this neutron sea, which we just can't notice because neutrons slip through everything. There's no charge, and there's no way we can contain a neutron sea. So this is why it looks invisible, even though it is quite possibly the densest substance in the universe, really. So now that we've solved that problem, so what are the other experiments that contradict the idea that the electromagnetic wave is like a sound wave. So I would say there are really only two experiments that contradict this view. So every other experiment says EM light is a wave. And then we have these two experiments that contradict it. So the biggest one that people will bring up is the transverse wave conundrum. And this has to do with polarization. So the simple argument goes that since light waves can be polarized and sound waves cannot, then EM waves must be something completely different from sound waves. And especially since it's polarized, that they're saying that if you go back to this original picture here, that it's picking up the transverse components. This is often shown as like a rope going through a picket fence, and so only the waves which fit through the slot are allowed to progress. And then they try and apply it to this picture, which you see if you applied this picture through a picket fence, it would basically filter out the, say, the magnetic component here, and then that would completely tear this thing apart. So you would predict that if you put this wave through a polarizing filter that worked like a picket fence, this would destroy the electromagnetic wave, completely filtering out, you know, at least the magnetic component completely. So if you think that the whole picket fence analogy makes any sense, well, think about it some more, and you'd see that it just doesn't make any sense. So let's go back and figure out really what's going on here. So I think that this rather naive conclusion that light can be polarized and therefore it's not like a sound wave is throwing the baby out with the bathwater, because I believe this can be explained. So the major difference between light and sound waves is really that light waves generally don't disperse or spread out from the source, while sound waves always spread out pretty much. Because light waves do not disperse, they can travel as a quote-unquote ray, which travels like an arrow in a straight line. So this is actually, I would contend, the only property that light needs in order to be polarized. It doesn't need to have any transverse components, such as is seen in the conventional view of the EM wave. We can easily observe this property with a laser beam, which is a narrow, thin ray that doesn't disperse. I mean, we can shoot a laser beam at the moon, and pretty much it maintains its shape. I mean, it has some dispersion, but not really. I mean, the main evidence of the non-dispersion is that we can see stars, which are billions of light years away. If light just at all dispersed at all that would just turn into a fuzzy blur, but it doesn't. Those light rays have to maintain their fidelity all the way across billions of light years to reach our eyeballs and still look like pinpoints. So this really gives it some of the properties that we would normally only associate with a particle, in that it travels as a finite-sized object through space. I mean, literally, a little, like a pulse of light would be localized like a bullet or a pencil, traveling through space, which only occupies a fixed radius and a length. So if you were to think about how light travels, it's literally traveling like a shooting arrow. It has a start, has an end, has a length, has a diameter, and it maintains that shape throughout its trajectory, just like a bullet. I think this is probably one of the confusions about, you know, they say light is a wave and it's a particle. I say no. Light is a wave, but it's localized like a particle. So it has some of the properties of a particle, but it's still a wave. And I'll get to exactly what that wave looks like in a little bit. But we're still looking at this whole question of how polarization works. So if light has this property that travels like a pencil, then we can easily explain polarization by looking at what polarization materials really are. So what polarizing materials really are is typically a stacked crystal structure, which is essentially sheets of opaque material with a gap between them where things like light rays can go between, but otherwise are blocked. So this is a little bit like stacking boards on top of each other, leaving a gap between them. So if we think of this stack of boards and we try to fire pencils at it at random directions, we can see that only pencils that are going to get through are the ones that happen to be exactly lined up with the gaps that are left by the boards. Okay, so yesterday I decided to go make a model of this. So I see, Bill, you've raised your flag. If you have a question, please put it in the chat. As well as Ian, if you have a question, please put it in the chat. I am monitoring the chat. But let's see here. Let's see here. How do I stop sharing this here? Okay. So here is my model of a polarizing material, which is just boards stacked onto each other. And so physically, this is what most polarizers actually look like. They take a crystal, they stretch it out, and you get a structure that looks basically like this. Now, what I'm saying is that a light ray is like this pencil. Literally, it's got an end, a front, it's got a fixed diameter, and it travels straight, just like a bullet would. So this is a polarizing material here. And if you have your pencils of light and you're just hitting it at random directions here, pretty much anything going forward or backward is going to be basically completely blocked. The only thing that's going to get through is that it has to go in exactly parallel to the slots. And so it can go up, it can be going down, it can be going straight through the slots. It has to be going only through, it's limited by going through the slot here, okay? So you start out with light that's going every which way, but the only thing that's going to come out there is light which just happens to be exactly in the same plane as your polarizing material. And even in mainstream, you can hear them, they'll describe it this way. They say this is plain polarized light, okay? Which means that instead of every which direction, all the light is then restricted to only a single plane, all right? So this is physically what I believe polarizers are. And this is, I think, physically what light is. Now, the premier feature of a polarizer is that if you turn one 90 degrees to each other, it completely blocks all the light. So how does that work? So we have one polarizer here. It's going to restrict it only to the up and down motion. Okay, so what happens, I then put a polarizer, which is horizontal, and this will now only allow light which will travel in the horizontal plane. So all the light coming out of your first polarizer means that all the light is only going this way. And when it tries to go through this polarizer, it is completely blocked. So therefore, this is a fully mechanical explanation for how polarization works. And as you'll notice, it has nothing to do at all with anything transverse wave. The only thing that light has to do in order to be polarized by such a mechanism is that it has to travel like this pencil, right? Just straight, okay? So let's get back to my paper here. Now that I've shown you how that polarizer works, you need to describe a little bit about Well, actually, before I get to that, there's another complicated thing about polarization, and that's something called circular polarization. Now, it's typically described by like this picture. We've got this crazy corkscrew thing going on with the so-called circular polarization, and it has to do with the electromagnetic field lagging behind the magnetic field, and we get this corkscrew. So circular polarization is a thing. So how can we describe that? Now, and I just figured this out yesterday, playing with these materials, because I took apart a 3D glass, and what a 3D glass has is a circular polarizer, and that consists of one of the lenses is actually made out of two things. This is a regular polarizer. Let's see here. I don't think you can see any polarization effects on that. Okay. And then they have what's called a quarter wave plate. These two things are actually sandwiched together, one up against each other. So theoretically, the result of these two lenses together is supposed to be a circularly polarized light. Okay. So, but what the action of this quarter plate is, which is just this clear piece here, is that I believe it's just to turn the plane of polarization by 90 degrees. And that's all it does. See so what happens is that if you have two pieces of polarizing material, and I don't know if you can see this, and you turn it so that they block each other like that. So that is because they're crossed to each other. What happens is that when you stick the quarter wave plate between it, what it does is it takes the plane, like if it's going this way, it will flip it so that it's going this way. So now when you insert this, actually you can see that the light then in fact just shines straight through. Let's see here. That's kind of hard to see. But instead of being blocked, that's completely blocked. This now will allow some of the light to go through. And I can see it, but maybe you can't. But it's a little bit hard to demonstrate this since I don't have a light source behind me. But that is exactly what the quarter wave plate is doing. And I believe actually it doesn't have anything to do with quarter wave. Doesn't have anything to do with the electromagnetic wave being retarded behind the electric field. All it's doing is that it somehow manages to switch the plane of polarization. And so what comes out of a so-called circular polarizer is still just an ordinary plain polarized light. It's just switched different angle. And so this has nothing to do with spiraling, things like that picture, nothing at all. And I would say that you really can't say that plain polarized light is anything unique, because it's just it's still a plain polarized light. And I would contend that if you were just given a beam of light that came out of, say, circular polarizer versus a beam of light that came out of just a regular polarizer, I would say that there would be no experiment you could conduct to tell which is which. The only way you could tell you have a circular polarizer in place is by knowing what the original orientation of the polarizer is inside your source. Without that, you would not be able to tell with another polarizer detector what you had. That could have easily been with or without a quarter wave plate, because the only thing the quarter wave plate is doing is just flipping the plane of polarization. That's all it's doing by 90 degrees. So I'd say nothing tricky about circular polarization. It's really fancy, but it's not. So, okay, so now that I've explained what circular polarization is, we really need to discuss what's my next point here, which is, okay. The next point is, how can light travel as a ray? Okay, like I said, I've got my pencil here. I'm claiming that light really travels like this, okay? And that way I can resort to explain how these things work without any transverse anything. I mean, a lot of people in the dissident community like to contend that, oh yeah, there's an ether, but it must be solid because that's the only way it can transmit a transverse wave, right? No, I think that's completely wrong. I've just shown that you don't need to have any transverse component at all in order to have polarization happen. It just needs to travel like a pencil, right? So how do we do that? So it would be, if we were to say that electromagnetic waves are exactly the same thing as, say, a sound wave, we would have to say that they would have to travel in basically a non-radiating fashion, right? So if we take your standard speaker for sound, we know that radiates out in a spherical pattern. And you really can't create, say, a beam of sound like you would with a laser, although I hear there are some experiments from the military trying to do stuff like that. But generally speaking, it's not really possible. The sound wave generally likes to radiate out, and you can't create a laser beam of sound. Although that is exactly what we need. We need like a laser beam of sound. We would need to have a speaker which only shot sound straight forward and only caused the molecules directly in front of the speaker to go back and forth and leave all the other molecules not in the beam alone, right? So that it wouldn't spread out. So, and if you weren't directly in front of the speaker, you should hear nothing, right? Absolutely nothing. You could be going full bore and you would not hear anything because all the sound waves would only be moving straight forward, which is what we need. So we need like a sonic laser is what we want. And actually, and if you were to observe the wave packet that's coming from this sonic laser, you would see that it has a fixed length, and it would be the same shape as the original speaker, round, and you would see that it literally travels as a rod. So there would be compression waves in here, but it would be just like this pencil. I mean, if you could color it a different color, you could literally see it pass through the medium like a particle. You would see it would just be just like this pencil, right? So that would seem to be a pretty tall order to have a wave do that, right? But I think this is exactly what we need to think of as an EM wave, using basically the same physical mechanisms as sound waves. So the idea being that this is a sound, this is going to be like a light wave packet, just like the pencil. It might contain individual waves in here that would, say, determine its frequency. But generally speaking, it has a finite width, right? It's very narrow, so it can fit through very narrow spaces. It has a length, and travels can be isolated as traveling through space. They have done experiments like this where they use ultra high-speed cameras, and they have actually caught, and then they just shoot a very short pulse of light through the series of mirrors back and forth. And they have caught it being in different places. I mean, literally, you know, they can see the pulse traveling as a pulse through the mirrors as if it were a particle, because that is the property of a light ray. So I'm going to justify this by saying that it's really the nature of the medium that determines the dispersion. So in air, we have all these air molecules, and they're constantly moving around and colliding. In fact, like the average speed of an air molecule in 70-degree temperatures is something like 3,000 miles per hour. These things are just incredibly chaotic. And so when you try and send a sound wave through that chaos, every single time it collides into another matter particle, it's going to send it into a different direction. But suppose that we froze the air and we put it in a very neatly arrayed order, all in rows and columns, right? Suppose we took our air and we did that. So if our air was like that, then if I then made a wave, like I pushed one particle on the left, then it would neatly only propagate to the particles and to its immediate right. Right? It wouldn't spread out. It would just go bump, right? It wouldn't go bump and then go it would go straight, right? And the wave would not necessarily disperse. And pretty much any wave action propagating through this neat array would only push its immediate neighbors and would not go careening off in some random direction like it were an ordinary sound wave. And also, I see some people have been putting up flags. Like I said, if you have a question, please put it in the chat, and I'll try and get to it if I see it. So far, I don't see any significant questions. So as I was saying, that if the medium were neatly ordered, it wouldn't necessarily cause a dispersion. The dispersion is really not a fundamental property of a compression wave. If given the correct medium, a compression wave would do exactly what we need it to do for our EM, which is for have it maintain its exact direction and not disperse. All right. So this is what I'm trying to say, is that in an ideal, well-organized, frictionless medium, a wave would not disperse. It would maintain exactly the same shape and width as it was originally generated with. And so I contend that this is what happens in the light medium. I did mention that we had this neutron sea, or I call this a photoelectron sea. This sea is so dense that it could be said there are no spaces between the particles for them to move independently one of another, right? They're just all jammed together, no extra space. So this basically eliminates the possibility of there being a lot of random motion to deflect waves like there would be in, say, a widely spaced medium like air, where each particle has a lot of independent velocity and a vector direction that can knock the wave in all kinds of different directions. So the reason why we can justify a light wave traveling as a ray is that the medium of the photoelectron sea is such a highly ordered array of particles which do not cause the dispersion of the compression wave. So with this justification of the light traveling as a ray and showing how this leads to the behavior of polarization, we can successfully explain why sound waves cannot be polarized, but light waves can be. And there is no contradiction. It's just a difference between the type of mediums. A medium which consists of randomly chaotic moving particles will cause, obviously, dispersion of the wave. But if you had a tightly packed, basically motionless, fixed array medium, then we would expect that the waves would in fact generate and propagate as these wave packets, and they would travel in a specific vector direction, and they would be, like I said, literally traveling like a pencil in a light ray. Once it gets set going, this can be from a star billions of light years away, it'll just keep on traveling through space as if it were a bullet. Although it's not a bullet, it's still made out of the individual compression waves, as if we had a sonic laser coming from this speaker, which only shoots the energy forward in only one particular vector direction. So, okay, I think I've beaten polarization to death there. So let's go on to the only other experiment that I know of that would indicate that that a light wave is something different than a sound wave, and that would be the photoelectric effect. Now, the significance here is that that no matter the intensity of a particular frequency of light, it just simply doesn't have enough energy to eject an electron from the surface of a metal. So this cannot be understood classically because if the EM wave is exactly like a sound wave, then it should have an amplitude. Right? You can have a little wave, or you can have a big wave, right? Of any frequency. So you should be able to turn up the amplitude of the wave in order to increase the energy to any arbitrary amount you want. So you should be able to create enough energy to eject electrons from the surface of a metal just by increasing that amplitude. But this doesn't matter. So no matter what intensity you raise a particular frequency, it just doesn't have the energy to eject an electron from the surface. So it was naively thought that the EM wave must be something completely different, since this cannot be explained classically. However, this is once again a needless conclusion. And I would say that it's critical to understand what is meant by increasing the intensity. Now, this could mean taking the same light source and increasing the amplitude of the wave. That's true. However, a light, especially visible light, which is what the type of light they're using in this kind of experiment, is produced by atomic processes where an electron has to jump a particular quanta and emit a quanta of light in the process. So if we think of this as like an ordinary compression wave, we would think of this as like a single pulse. So you'd see, as light is emitted from this electron transition, you'd see a pulse, boom, right? Boom. Every single time the electron would do it, you'd see a single compression wave, like a pulse. So the length of the pulse would determine the observed frequency. It could be boom, or it could be boom. But since light is generated by atomic processes, and that happens at fixed distances, however you think that happens, it would be expected that the amplitude of these waves would be a constant. I mean, if you have the same thing, if it's going from A to B, it's got to do the same thing every time. You can't make a bigger amplitude. It's whatever amplitude it's at, right? That sort of thing would be fixed. So since this light is generated by atomic processes that happen at fixed distances, it would be expected that the amplitude of these waves would be a constant. So the only way you could increase the quote-unquote intensity would be to increase the quantity of wave packets that are generated by the source. So we would see this as, we see this in our eyeballs as greater intensity. but only because the number of wave packets has increased. The amplitude of each of the individual waves is absolutely identical and can only contain a fixed and a limited amount of energy. And this is another reason why people think that the energy of a photon is quantized, and in fact it is, but it's still a wave. It's not an incoming physical particle at a fixed velocity. So this is why if the frequency isn't high enough, each wave packet is still incapable of providing enough energy to inject an electron from the surface in the photoelectric effect. It doesn't matter how many you have or how often they hit, they just don't have enough energy to do the job. So this explains the photoelectric effect by showing that the waves that are generated are created with all the same amplitude. So increasing the quantity or quote unquote intensity has no effect, and we would predict that. And this is all easily explained as a property of the EM wave, which, as I contend, is just the same as an ordinary compression wave like sound. No exotic explanations are required to explain either the photoelectric effect or polarization. So we come to the end of my paper here, and it can be seen that the EM waves in general can be seen as being caused by a simple compression wave, which is exactly the same mechanism used to transmit sound waves. So despite being called electromagnetic wave, the EM wave has absolutely nothing to do with the electric or magnetic field. It can be seen as a simple compression wave propagating in the very dense and non-dispersive positive electron seed. The only two contradictory experiments involving polarization and the photoelectric effect can be trivially explained if we understand that EM waves travel as rays and light and is generated by atomic processes which lead to fixed wave amplitudes. All right, so that concludes my paper. Now, so I want you guys to prepare your questions. I need to go grab a drink of water, and I will be right back. So if you have a question, please raise your flag, and we will go through your questions in order. Okay, questions, and feel free to disagree with me, since I just blasted up this paper in just like 2 days, and I made a lot of assumptions, and some of them could have been wrong. So first we have Ian.
Thank you, Franklin. Well, thank you for the presentation, because I only saw your paper about 20 minutes before the presentation, so went through it very quickly. But you've expanded on that quite well, so thank you very much. I've got some comments and questions, I suppose. Well, a general point first is that basically, I'm tickled that you've basically accepted my thesis. But you, as you say, you've actually gone a bit further. You've, taken not merely there to be an analogy between sound and light, but that they are basically identical. Now, you've obviously justified this quite cogently, and I have an open mind on the matter. But I feel that one mightn't have to go to that extent at present, because as I think I've shown that from the classical theory of electromagnetism, you can derive the perfect analogy between light and sound without saying that it is actually a physical compression. You can say there's an analogy between the electric stress, if you like, and the magnetic strain. Now, the conventional transverse nature of the electromagnetic wave, although actually you possibly contest that it's electromagnetic at all, but the transverse nature of this, if it is electromagnetic, comes basically from the Gauss divergence laws. So it's actually even more fundamental than the Maxwell equations. Maxwell equations would be based on that. And there are things like Faraday rotation, which you put a magnetic field and you get this sort of rotation of the wave, and there's a Thomson scattering where you get a sort of a scattering when, say, an electric charge, an electron, actually collides with the electromagnetic wave. This can be considered basically a low energy Compton scattering. So there may be two things that one might have to explain or explain away.
So you had Thomson scattering, and what was the name of the other one?
Faraday rotation. So Faraday rotation is the B one, and Thomson scattering is the E one, if you like. So you've postulated a sort of a more orderly ether. I postulate an ether, but I don't go as far as you as to ascribe particular properties to it. But you've ascribed a more ordered system rather than the random movement that we have in ordinary gases, which obviates polarization. So basically,
I wanted to make clear that it's not as messy as a gas, but to be more like a liquid, but it's not as ordered as the crystalline structure of the epola. So there was a comment about me supporting the epola, and it's like, no, I still believe the epola is mostly right, but its idea that space is a solid structure, once again, motivated by people's irrational needs to support a transverse wave, is actually not necessary.
Yes, Cornelis left that message. Okay. I mean, all I would say maybe is I think your explanations, while cogent, are a little strained. I mean, there might have to be other reasons why you accept your model first before maybe trying to have to explain these things away. I mean, if you're incorrect and the electromagnetic wave is thus and has transverse electric and magnetic varying properties as given as derived from the Gauss law, well then probably your explanations are unnecessary. One other thing which seemed to be a little new, by the way, is you talked about the...
I think it's backwards. I think that Maxwell's explanations are unnecessary in light of my explanations. But somebody's wrong here.
That's right. Who do you take first? We might have to do a lot more experiments and see whether there are contradictions between your two systems and which one gives the more correct results. I said that recently, actually, in regard, I think it was maybe with conversation with Bob Gray there, in regard to the Weber alternative theory as well. I mean, you could argue until you're blue in the face about this, but really we need more experiments to see whether Maxwell or Weber would be nearer the truth, and then we can sort of drill down a bit further. So that's my general comment. I mean, as I say, I agree with actually your thesis. You agree with mine, but I think you've gone a bit too far, and I need a bit more convincing before I'd accept that. Thank you for the present, anyway.
Okay, great. So, Michael Anteski, raise your flag.
I'd like to draw an analogy not with sound, but with ocean waves, with my ether model. My ether model is based on the idea that it was originally a universal oscillation, which transitioned to a universal vibratory ether. Well, with the vibratory ether, the outward vibrations energically align, and in the presence of energy, you will have entrainments and other linkages of the ether units, individual vibrating ether units. And now if you take the ocean, you have the surface of the ocean has these little waves, and deeper down you have surges of energy, currents, and this and that. But at the surface, the density of the vast sea is not present, and you get these small waves that go back and forth. But then, as you come to the shoreline, the waves become accentuated. You lose the attenuating effect of the deeper water, and the amplitude of the waves increases. Now, to draw an analogy with the ether model, you have a vast sea of very tiny elemental ether units, and then all of a sudden, you could have, in the presence of an energy source of energy, let's say an electric current, or let's say a source of light, photonic or electronic energy in an area, there would be an increased transition of ether to a quantization of the ether, and the formation of larger and larger units via entrainment and other linkages. And so the wave effect would be increased. It would be like a shoreline effect. You would see these really dramatic wave effects, because it's like the waves way out in the deep, where the ether is so dense that the waves are smaller. But
that's an interesting observation. Although I would try and take you back to what we're talking about, which is the nature of the electromagnetic wave.
Well, that's
and
what I'm talking
about.
What
you just said seems to have no relevancy to the conversation. So how does this relevant to, whether electromagnetic wave is this magnetic electric thing, or is it like a sound wave? How is that related?
Well, the energy that we observe is from our vantage point, which is the quantum forces vantage point, or where we have vectors and spin and these other mechanisms. Whereas what I'm saying is that this is a shoreline effect. These waves EM waves that we see, represents a shoreline effect of transition of vibratory ether forces into quantum units, like electrons in the case of an electric current, or photons in the case of light. And it's a shoreline effect? It's a shoreline effect. I'm saying it's a shoreline effect, and the reason we see it so much as a wave is because the wave effect is accentuated by the transition from all these smaller units into to the larger quantum.
I mean, you're talking about the reception of electromagnetic wave. So when a star sends its light all the way to Earth, you're saying that it's like a shoreline effect when it finally hits our eye. Is that what you're saying?
Well, I'm saying it happens all along the whole length of the ray. There's a transition between etheric vibrating units with a photonic vibratory pattern to electrons all along the way. But when it reaches Earth, the region of our sun, there's more of a accentuation of the photonic transition because of the energy. Because if you have more energy, that's when the alignment of the ether and the entrainments and the linkages and the formation of the quantization thing. I mean, that's my theory. It's my ether model.
All right. So, Bob, you have raised the flag.
I think Harry has raised his flag much earlier. We should try to go in order. But yes, I have raised my flag. I have a comment.
Go ahead, Bob.
Thank you, Harry. I think there's a distinction between an electromagnetic wave created by taking a charged particle or charged body and raising it up and down, oscillating like in a dipole antenna, which radiates in all directions, and an electron in an atom which de-excites from one quantum state to another and emits something, but that's only in one direction. And yet the electron, you could go and say from a higher state to a lower state is a certain movement, but what's generated is not an omnidirectional wave, but a very directed wave. So I would suggest thinking about distinguishing the two cases. And so there may be two different kinds of waves propagating. One, like in the dipole antenna, I would suggest is, as you were saying, maybe like sound waves, and it goes in all directions, whereas the transition of an electron in an atom may generate a soliton or something else, a more particle-ish kind of thing that is very unidirectional, has a direction, and is not emitted in all directions. And so maybe you got to think about, maybe there's two different kinds of waves involved in quote-unquote electrodynamics. That's my comment. Thanks.
Yeah, actually, I would totally agree with everything you said, because I believe that there is a distinct, a very large distinction between EM waves generated by atomic processes and EM waves generated by, like you said, dipole antennas. Although I would say that that all EM waves are directional, but in the case of, say, a dipole antenna, you have billions upon billions of electrons, which I see as being literally pushed out and in of the surface of the dipole antenna. And so it's only just directional because you are literally sending these EM wave packets at every single direction out of your dipole antenna. But even with a dipole antenna, when you're trying to receive the wave, if you think of them as being like these tiny little bullets coming out, they're still better received by an identical receiving dipole antenna of the same shape and type, because there's more possibility of intercepting these things. But the other difference between waves generated by dipole antenna is that I believe that the amplitude in those cases can vary, that the amplitude of a radio signal can genuinely vary versus the amplitude of light produced by atomic processes, which I still think has to be of a fixed amplitude, and it's of a fixed vector direction. So like, for example, if you see positron-electron annihilation, they generate two gamma rays, and these gamma rays can be said to be going in a particular vector direction, and they actually hit the detectors in one spot, as if they were a bullet. But yes, I agree with you, Bob, completely that, yeah, there are these two cases, and but I think that would be the subject of another paper, which is what is the difference between visible light and radio waves. So now, Harry, you did raise your hand as well as Bill. Raise your flag. So, Harry, why don't you go ahead?
What is your motivation for this? I mean, it's a big, long dissertation. Why are you insisting that we have to throw away a satisfactory? Why are you insisting we need to throw away a satisfactory model that served very well for over 100 years?
Because it's wrong. No matter if it...
Okay, so do you have some proof that it's wrong? What's your proof that it's wrong?
Oh, yeah.
Well, once again, my entire paper is proof that it's wrong. Proof that it's wrong is our inability to measure the actual rising and falling electric and magnetic field.
Let me stop you there. What proof do you need?
I need a proof, like you put a squid detector along the transmission length, and you should be able to do this, but have a transmitter at one end, generate a low frequency radio wave, and along the path, you should be able to predict exactly where you're going to see the maximums and the minimums, and show me the time varying magnetic field, for example. That's something we can measure.
So you're saying that you don't think that an electromagnetic wave is composed of electricity and magnetism?
Exactly. I believe this is my contention. Has nothing to do with that. That's all in people's heads. That has absolutely no physical reality.
So you're saying that in effect, basically, that light is not electromagnetic.
That's right. Light is not an electromagnet. That's my main point. They may call it
what about radio
electromagnetism,
waves?
but it has nothing to do with
Radio waves are not electromagnetism as well?
Yes, radio waves do not have anything to do with electric or magnetic fields propagating through space. Nothing. It's just like sound waves. I'm saying that it's like a sound wave. It's just a compression and rarefication of the medium. That's what we are seeing in the EM wave. That's as radical a change as you can possibly get. I understand, but that's what we hear in the CNPS.
What is your need for this radical change? I mean,
the need for the radical change is because this conception of the EM wave as this electromagnetic field does not make any intuitive or logical sense.
Well, it makes a lot of sense to the people for the last 100 years. You seem to be the only objector to it.
Yes, that would be right. But then again, people didn't object to the idea that the Earth was the center of the universe for thousands of years. But that didn't mean it wasn't wrong.
Well, that's not really an argument. I'm
just saying that it's not an argument to say that everyone agrees that this is true.
Do you agree that if I put a detector that detects electricity at the output of a radio antenna, that I will detect power at the output of the radio antenna?
Well, we know that's trivially true. The question is, how does that happen? We know what happens at the endpoint.
That's not what I asked you, Franklin. I asked you whether or not you agree that if I put electricity on the transmitting antenna, okay, well, what Marconi did and what they did in the very early days of radio was they charged up an antenna with a high voltage of electricity. So they put electricity on the antenna.
Yes, but that only proves that electricity generates EM waves.
Excuse me, I'm talking now. And at the other end, okay, Marconi discovered that he could detect the electricity when they created an oscillation on the transmitting antenna, which was electricity, okay, powered by electricity. He got electricity at the output side. Do you agree with that?
Absolutely. That's what he did.
So then why do we need your model?
Because you can say exactly the same argument that I apply electricity to the speaker, and then I have a microphone, and I recover electricity from the microphone. So does that mean that the wave traveled through this electro and magnetic fashion?
Probably won't be hungry.
So you're denying that the phenomenon is a phenomenon of electricity.
Right.
No, I'm denying the phenomenon that this wave travels as a time-varying electric and magnetic field, which are traveling orthogonal to each other.
I mean, I don't really see the need to do that. I mean, it seems to me that's fairly well established by experimental facts. So why are you denying something that's well established by experimental facts? I don't see the need.
It's not established at all. This is what I'm kind of content, that nobody can show me any physical experiments that can recover the time-varying, say, magnetic field from a traveling electromagnetic wave, which you would have to.
I explained it to you, Franklin. I just explained it to you and how they discovered radio and how it works. I just explained it to you. So
and I just gave you the analogy that completely blows that away, that I can do exactly the same thing with an ordinary speaker and an ordinary microphone.
This basically is not logical, okay?
No, it's perfectly logical. What's illogical is this, how can there be a magnetic field or a charge or electric field without there being any charges? We know these electromagnetic phenomena travel through space through perfect vacuums where there appears to be no charge for there to be there. I mean, it makes no sense that we have the electromagnetic wave as it's pictured, where it rises, and they rise in phase, right? The electromagnetic equations say that the magnetic field should follow the electromagnetic. I mean, you have a rising electric field, then it's followed by a magnetic field, and the magnetic field can then generate the electric field, but those have to be out of phase. So it makes absolutely no logical sense that you could have a magnetic and electric field rising and falling at exactly the same time. And what happens when it goes to 0 point is what I'm saying. That it's dead. When electromagnetic and electric fields go to 0, I mean, it's really 0. There's nothing there. But then somehow it comes back from the light, from the dead, and it goes back to a maximum and then goes back to 0. There's no way they could possibly regenerate from each other when they hit 0. So I'm saying that entire picture is just on blackboards in your head.
I think what you're saying is you don't understand it, and so therefore it's wrong.
No, it can't be understood as logical inconsistencies that make
I
it
understand it.
wrong.
You just don't seem to be able to. So I don't really understand, from my perspective, I don't understand why should I accept something that I understand is wrong because you say you don't understand it. I don't really see that.
If you were to look at what you think you understand,
anyway,
you would find out that you don't understand.
I think we've reached the crux of the matter, okay? And I don't really see there's much point in discussing it further as far as I'm concerned.
All right. Well, let's go on to
let's let other
Howard
people
Gowdy has
talk.
a question.
Hello. Hello.
Hello. Go ahead.
Yeah. Can you hear me?
I can hear you.
Yes. Let me make Franklin, your paper seems to be well written, and the first diagram that you have in this paper, you have a chain of waves there where the electromagnetic wave and the magnetic component of that are right angle to each other, and they move at right angle. That is what the experiments have understood for almost the past century now. And what you have in your paper, I've read through this paper, and it seems to be well written, but your hypothesis seems to differentiate from what you have written in this paper. The thing here is, I believe that it's misunderstood in your hypothesis, but let me say this to you again. And I'm Ed Dowdy, just in case some of you guys may not know me. And I have a website, extinctionship.com. Go to my website, extinctionship.com, and I place a lot of my papers on there and my presentations that I have done. And Bill Lucas is very familiar with some of the stuff that I have done. But let me say this. When you look at a wave, electromagnetic wave ray, what they call RAY, a ray, that ray is not like a chain, like a very long chain that you span from one tree to another tree, a chain that's a mile long, for example. That's not what this is all about. I believe what happens is that you have what is known as wave packets, and packets, that is packets of waves. Some people may want to call them photons, but some people have problems with photons. I have a problem with photons, the way the photon has been defined over the years. Some people have a definition of what a photon is, but a wave packet is easier to explain. What happens is that when an atomic system emits what is known as a wave packet, that is a quantum that is being released. That electron, actually, that the atomic system actually shoots out, right, a wave packet, and it is quantized, right? It is quantum energy, and the higher the frequency, the higher the energy. The lower the frequency, the smaller the energy is. Now, electromagnetic waves like broadcast stations and kilohertz, or even low frequency, which the Department of the Navy used to communicate with the ships and submarines and so forth. You can build a very large antenna, a very powerful antenna, and you can shoot a long wave to the moon. And it could be received on the moon if you can get by the north. If you have enough energy, you can do that. Electromagnetic waves, it goes from microwaves, to gamma rays, even the higher frequencies. They get all kinds of electromagnetic waves from out in deep space. And what happens is that when you look at what is known as a ray of waves, right, coming from let's say what is known as the neutron pulsar stars, for example. Some of these pulsars are sending out very sharp energy, so sharp and so precise, even the atomic clocks on Earth have difficulty keeping pace with these things to find out how accurate they are, because it's so sharp. You can position our relative motion of Earth and even our laboratory relative to some of these systems. Electromagnetic waves are electromagnetic waves, and they're all electromagnetic waves as far as we can see. Now, that very first diagram you'll have in your paper there, where you have the blue wave, that is electric wave that is in the what is that? You have the X and Y direction, right? The blue wave is in the X direction, and the red wave is in the Y direction, and they are right angled to one another. And that's a very long thing. This is what the experimenters understand. How they explain it, that's a different thing.
No, I would claim that the experimenters have found no such thing. This is all theoretical physics.
Let me finish that. I'm not disagreeing with you with your hypothesis. Your hypothesis is difficult for me to understand. But the experimenters, when they go in the laboratory and you teach your students, that the magnetic component of that and the electric component of these waves are at right angle to one another, and they move at right angle. The direction of motion is at right angle to also going from in the Z direction. That's the motion, right? But
and the experimentalists have never actually found that.
Let me finish. Please, let me finish. But when you design an experimental apparatus, the way I can detect only the magnetic component of that wave, and I can also detect only the electric component of the electric component of that wave. I've done that in Germany when I did nuclear magnetic resonance experiments, and I had what is called right angular polarization or left angular polarization. All these instruments are designed that way. The easiest way to explain it is the way you have it in this diagram. I don't disagree with that diagram. And your paper is one thing, and what your hypothesis is doing is something different. And that's where I disagree with you. So you're looking at long waves coming distant stars, and these pulsars have been going for millions of years, and they're sending out long waves going in approximately all directions, but it's going in a straight line, very straight line as far as we can tell, and it's coming to our telescope. And this is what I'm saying. So I just want to make that point clear. Go to my paper, and you can see I talked about this same principle, and I talked about this. And I'm going to click off here now and listen to your comments. Okay? Thank you very much.
Okay, so first of all, I want to make it absolutely crystal clear that my hypothesis that the EM wave travels as a compression wave exactly as sound, and that this picture you see here of the electromagnetic wave having independent rising and falling magnetic and electric fields is a complete fantasy, okay? So everything in my paper, I believe, is consistent with that hypothesis, okay? Now, most of what you said, Dodie, I completely agree with, that light can be generated at different amplitudes. It travels in a straight line. And a lot of that is what I explain in my paper. I mean, these are things that people know about, all right? There's no controversy over how those things happen. The controversy that this particular paper addresses is how this thing actually propagates. Now, you have claimed, and this is an interesting claim, I would challenge you that you said you have actually measured the rising and falling, say, magnetic field. But I don't think you have, because you said you measured the polarization, okay? That's different, okay? Measuring the polarization has nothing to do with measuring the individual rising and falling fields. As I explained to Harry, the only experiment I would accept is if you have an independent, like you said, a string of independent magnetic field detectors. And then on one end of your experiment, you send a fairly low frequency EM wave through that box, and you show me that along the detector line, you can say there's one that says maximum, there's one that's going down, there's one that says minimum, one that goes out, and we would predict experimentally that if EM waves actually travel this way, that you can create a standing wave in there, that as it travels, that you can see this time-varying magnetic field, not polarization. If you're measuring polarization, you're cheating.
Oh,
you're making another interpretation upon interpretation.
Okay, can I make one more point? One more comment. Go ahead. One more comment. Then I'm one. What the words that you're saying that's coming out of your mouth? What you want to say is the magnetic component of an electromagnetic wave, or the electric component of an electromagnetic wave. That's where I think you're getting confused here. The wave doesn't actually look like that. If you could see that wave propagating through space, you could actually see it. But there are instruments. I can tune my instrument in Germany when I was working in the laboratory in Germany. I can detect only the magnetic component of an electromagnetic wave, and I get so much energy from it, right? And I can detect also the electric component of electromagnetic wave. You can tune the instrument, and you have to rotate it 90 degrees in order to look at the other component. You have to actually physically rotate this thing about the z-axis, right? And you can see one to the other. And if it's a right circular polarized wave, that thing is actually turning, right? It's actually spinning. You show a diagram like that. That's real. That's in the laboratory. You can see that. You go in the laboratory.
That's very interesting. That's very interesting. So if that was true, that would prove me wrong. But can you give me what's the name of the experiment I should look for?
That's a right angular circular polarized instrument. It's in all laboratories. It's in every physics department in the United States of America. You can go in any physics department, and the student, a good graduate student, can show you that thing.
Just tell me, what can I search for on Google to find this experiment? In as few words as possible.
Go to right circular and left circular polarized light. Go to it. Go on Google, and you can find it on Google and on YouTube, right? And
I during my research for this paper, I extensively researched circular polarization, as it was one of the few things that I was not able to explain. But during my investigation of that, I did not find any evidence of what you speak, which is an instrument that can detect either the magnetic or the electric field. Circular polarization has to do with creating, like I said, I have a circular polarizer I demonstrated here today. This is a quarter wave plate. And I have regular polarizing materials. And I demonstrated what a quarter wave plate does, which is to flip the plane of polarization by 90 degrees. Experimentally, that's what it does.
There is a crystal that you can put on a plate, and you can squeeze that crystal. You can put a mechanical pressure on that thing, and you can cause that crystal to be slightly deformed a little bit. And you can cause that wave to slow down around the z-axis and spin it. That happens. That shows you that there is something going on there in the real world, right? How you
it's changing the plane of polarization. That's what this quarter wave thing does. But I'm still looking. I mean, I'd be very interested in finding that experiment that you says that rotates. What's the name of that mechanism that rotates?
It may be rotating in a sense when you take the hypothesis of the wave, and where we understand the hypothesis of the wave, looking at it in 3 dimensions, right? The x and y being the wave component, and the z direction being the direction of it. How you explain it is your hypothesis again. That's where I have a difficulty. I think you said just a minute ago. You sounded like you were very reasonable the way you said that just a minute ago. I agree with that. But then again, you say something else. And I think
well, the only things that you could possibly be recovering is, say, the vector direction of the ray, really, in my hypothesis, because there is no recoverable.
Ray, what do you mean? What do you mean by ray? When you say ray, R-A-Y, what do you mean by ray?
I mean a ray that the EM wave propagates like this pencil I'm holding. Mm-hmm. That it is still a compression wave phenomenon. Well, this pencil could contain like 10 individual wavelets in there, but it maintains, it's very thin, pencil-like, and as it travels through space, maintains its structural, its spatial integrity.
Now, sound needs a medium in which to propagate. Electromagnetic waves does not need a medium. You can have an ideal vacuum, a really high vacuum, and then electromagnetic wave is fine, right? Electromagnetic
no,
waves,
that's a logical contradiction.
A series of packets. When I talk about a series of packets, a whole bunch of packets, a lot of them, right? You can't even count it. There's so many of them, right? It seems like a chain, but it's not really a chain, right? So that's where I go. Okay, I'm going to listen now. Okay, guys. Thank you.
Well, see, I would point out that to have a wave, but no medium, is a logical inconsistency. Literally impossible. It's like saying black is white. To say that electromagnetic wave can travel, when we can recover the amplitude of the electromagnetic wave, we can convert it to sound, in fact. Like it takes 60 hertz radio wave, convert it into sound, and which means it has exactly the same properties, but we know in order to be a wave, there has to be something has to be varying. That varying thing has to be a medium. So to say an electromagnetic wave travels without a medium is it's a logical inconsistency. This is what I call, in science, it's doublethink. That in one way we know that a wave requires a medium, but yet we perfectly accept the fact that the electromagnetic wave doesn't have a medium. That is doublethink, right? The only reason why you believe that is because it's been pounded in your head, even though it's an obvious contradiction to what we would normally associate with a wave. I'm just trying to get people to recognize.
Pardon me, Franklin, for interrupting. That's your error in thought. You don't understand that, and you don't understand how a wave cannot have a medium because you insist that a wave must have a medium. Okay, that's logically in thought on your part.
No, I would claim the exact opposite in that.
Well, of course you did, because you refuse to accept that it's an error.
Because it is an error. It's a clear logical error.
On your part.
Then you explain to me how a wave can travel without a medium.
It's explained in electromagnetic textbooks. You just don't understand it.
No, I'm challenging you to explain it because I know if I challenge you to explain it, you can't.
Deflecting doesn't work, Franklin. You can't.
No, you have no explanation.
Deflect. That's all you've done through this whole discussion. Unfortunately, you don't understand it. You've made an assumption about waves. You say waves have to have a medium. You've made that a principle of thought, and therefore you're trapped in that principle.
That's right. I'm trapped in the principle of logical deduction. As opposed to people who can double think, which means they can completely ignore logic. I actually want to hear from Bill, but Bill is always talking about
Franklin,
lots
please
of
just
logic.
Let's move on to another subject. Okay, you just don't get it, and that's unfortunate. Let's just move on. Let other people talk.
Well, this concept of doublespeak, I actually think is very important, where physicists accept things even though they know they logically have no explanation. And when they start doing that, then they have gone off the rails in science. So I know, Bill, you had your flag up earlier. I was wondering, what was your comments?
I have some data to present for the concept of what waves need to travel. Arthur Compton received a Nobel Prize for finding the wavelength of the electron experimentally. And he continued to do experiments, and what he found is the wavelength of the electron is the circumference of the particle when you do low energy electron scattering. And from that scattering, you can determine the size of the electron. They did that at the laboratory where I worked when I got my PhD, the Space Radiation Effects Laboratory. It was the world's most advanced laboratory, scattering accelerator laboratory, for 15 years. And but Arthur Compton's last graduate student, he was still having people do experiments. His name was Winston Bostick, and he was able to disturb the electromagnetic field and make what is called a soliton. It's a standing wave in the electromagnetic field. He was surprised to find that if he put this soliton into the beam was hitting it, of an accelerator or into a reactor, that nothing in the beam or the reactor could destroy it, could break it. So it was considered uncuttable. And then Arthur Compton showed that our concept of charge is a mathematical approximation to the fields of a soliton, and that all elementary particles, including the electron, are made of multiple solitons. And I was able to take that work and to make a theory of elementary particles showing that the electron is made of 3 solitons, and I showed the soliton structure for all of the 96 major elementary particles.
Well, that's describing the structure of an electron, but we're not really describing electrons here.
Let me finish.
I'm more interested in what you think the electromagnetic traveling wave is, not what electrons are made of.
The experiments were done at the University of California at Berkeley on the properties of the electric and magnetic fields. And they found there were 13 properties. And one of those properties of the field is that it has tensile strength. So the field is the medium of the electromagnetic wave and sound waves and all other types of waves. So they showed that experimentally, and that is published. And they're both books and papers in scientific journals on that. And it's been confirmed at many universities. So, so we have a conflict here. We have one party is saying that the electromagnetic field is the medium, the ether, and the other is saying, oh no, you have to have particles, and those particles exhibit electromagnetic fields. But what Arthur Compton and his graduate students showed is that electromagnetic field is that we call a particle, the soliton, is really just all field. There is no such thing as an electric charge. It's just a mathematical approximation so that you can describe the field that a soliton has. But a soliton is like a cyclone, or which is a disturbance in the case of the cyclone, the atmosphere, and it has a funnel. The cyclone has a funnel, and it has other parts to the structure that go out to great distances. But we don't approximate the funnel like we do charge and say, well, if you understand the funnel, you understand everything about the cyclone. And but that's the comparison. And what we find is it's the electromagnetic field between the structures of solitons that produce sound waves and these other types of waves that we've been talking about.
Yes, certainly that would be the contrast. I mean, this paper strongly argues in favor of the concept where there are physical particles and that the field is not fundamental. I mean, to me, to say that the field is fundamental is a logical inconsistency, because if you have a field, that means you can put an instrument in it and measure some physical property, like the intensity of the electric field. That means something physically is changing, and the only way that there could be something physically changing is if there's something physical there, which goes back to the fact that this field, has to have something behind it, like a physical sea of neutrons. So I see a comment here from Mitch saying that the neutrons would take up space and they would have mass, and that you would think that would make it easy to detect them. So, but I would challenge you and say, really, how would we detect them? How would you detect a sea of neutrons around you, right?
Well, they're very easy.
They travel straight through you. There's no difference.
We
Go ahead.
Accelerator experiments all the time, and the neutron does not have a net charge, but it does have a spin and a magnetic moment, and both of those can be measured. And so we have no trouble detecting neutrons, and we can also see their decay. And and by the way, there's no longer any evidence left that there's a neutron in the nucleus of the atom, because since the mass of all the nuclear isotopes have now been measured, all 3,500, by NIST to 8 significant figures, the binding energy of the neutron, which is 8 MeV, is missing from every nucleus that we know. And
yeah, so, well, that I would agree with that. That's why I would say that within the atoms, what you're really looking at is just a positron electron, and which held together by nothing more than a Coulomb static force, 1/r². There's no special binding force for the neutron. But the thing is, I would contend that we have set our experiments to basically ignore the most obvious thing, which is this neutron C. Now, I would say that the neutron, like I said, I call the positive electron different from the neutron, because I believe the neutron is something that pops out of the atom and it has a particular independent velocity, right? It's essentially a positive electron, but with velocity. Fundamentally, every neutron we can detect has to have some velocity, because I would predict if you take a neutron and you slow it down, you will find that some of them will just meld back into the neutron C, and you will never see them. They literally disappear, and there are experiments where they have this. I mean, they're the missing neutrons. They just cannot explain some significant fraction of neutrons just disappearing, right? And I would predict that sometimes they don't decay, because the only way you can get a decay to happen in a neutron is it actually has to collide with another positive electron in order to form a proton and then a free electron. And that's also the reason why a neutron takes so long to decay, because it takes this very rare collision in order to actually see it turn into anything else. But the most likely thing for a free neutron to turn into is for it to just meld back into the neutron C, which, like, I would contend there's no experiment that we could do could easily see this mass. I mean, one experiment you could say is that, well, if there's that mass out there, we ought to be able to break those neutrons apart into their constituents, which would be positron electron, right? We should be able to do that. But in fact, we can. It's like, this is called paraproduction. If we send enough high energy gamma rays into a system, when it hits an atom, it causes such a shock wave that it does in fact create positrons and electrons. Or if we collide two particles together with enough energy, that too rips the positrons and electrons. As we see positron electrons sprouting out of nowhere, in these experiments. So yeah, we have actually detected these things being ripped out, but like I said, neutrons are very hard to detect. They interact very little with ordinary matter. If you had a jar of neutrons, it would look completely invisible.
We detect them and we form beams of neutrons by using the magnetic moment and the spin magnetic field. There's two
Yes, we do.
Fields,
and those are easy to detect.
And we can take a whole bunch of particles. We can take, say, a proton and bang it into carbon and make all kinds of particles. And then we can use electromagnetic fields to separate them out and get just the neutrons.
Yes, you can do that. Like I said, my contention is that those neutrons at all times have to come out with significant thermal velocity.
And these neutrons, we can control the velocity by using electromagnets, because we can get hold of them with the electromagnetic field, because they have a magnetic moment, and they have
and this is what happens.
Magnetic spin.
That if you slow them down enough, some of them disappear completely.
Well, when we do experiments, we can keep track of every single one.
Yeah, and I'm telling you, you'll look at the neutron anomaly experiments. You'll find there are experiments where, yeah, they can keep track of every one of them, and they find out some of them just went missing, which is something I would predict would totally happen.
Well, at the Space Radiation Effects Laboratory, which is the world's best laboratory for these experiments for 15 years, taking the place of CERN, because CERN's equipment did not work very well. They were able to detect these things, and they were wondering what would happen if we went into space and we had this media of space, and if it were neutrons or whatever particles it was, they would have an effect on the health of the astronauts. And so what they were doing is they were reproducing what they could measure from our satellites that would be in space, and they were trying to find out what the effect would be on people and animals. And so that was their goal for 15 years. And they were able to measure these things. They were able to publish papers. I published a number of papers related to that. And it's something we can measure. But I don't think you're aware of that being done. I don't think you realize all the kinds of detailed experiments we can do with neutrons. We can make a beam of them. We can.
Yes, I agree with all of that. None of that contradicts anything I've been saying. None of that.
Okay, we measure every form of decay of the neutron.
Yes, and like I encourage you to look up this neutron anomaly, where we have very sophisticated experiments where it's like, well, some of the neutrons just completely disappeared. We don't know where they went.
But we didn't have that problem at the Space Radiation Effects Laboratory, and we had the
well. Now we do.
You may find another laboratory that's not as good. They can't keep track of them because they don't have all the right equipment.
Well, now we do. I mean, perhaps now we have reached the level of accuracy where we can significantly say that, like, yeah, 2% of the neutrons just completely disappeared, and there's no way that we know. There's no way we can account for them. Other than my hypothesis, which is that they just melded back into the ether.
Well, can we talk about electromagnetism?
Well, it looks like we're kind of at the end of our discussion here. We're almost 9 a.m. I see Ian has raised your flag, so I'll let you have the last comment, and then I think we'll have to wrap things up.
Thank you, Franklin. I'll be very brief because I've just got 2 points I'd like to address with regard to the speed of waves. Now, if you accept, which I think we both agree, that the speed of a wave is given by the square root of the elasticity to stress divided by the resistance, or in other words, inertia, the resistance to strain. Now, so in your theory, you should be able to ascribe to the ether, if you like, what is the effective bulk modulus of elasticity, and also what is the density, because there are an infinite number of combinations, but your theory should be able to ascribe values to that, which would be most interesting. My second
the
question...
calculations done by Epola, while I disagree with their physical layout, I agree with all their calculations showing why the speed of light is and the density of the electron-positron sea. I agree with, so if you're looking for specifics on that, you'd have to just look at the Epola.
You take their values. Okay. Well, I'm not sure if you've answered my second point then. My second point is, how come that the inverse of the electric permittivity, which is measured independently, electrically, divided by the magnetic permeability, which again is independently measured in the laboratory, and you get the square root of that, you get the actual speed of the electromagnetic radiation. Is that just a coincidence?
No, I think, as you suggested in your paper, that there are direct analogs to the magnetic permittivity. It would have to be like the magnetic permittivity would have to be equivalent to, say, density, and that the electric field strength is the other one, basically. And that what we have there is that, they're proportional to one another. So there's this proportionality. The formulas are kind of giving us a hint as to what those things really physically are, that the actual density of this ether is directly measurable by, say, the magnetic permittivity, as you say. That's permeability, that is just a property which increases proportionally. It just happens to be more handy for us to measure it that way than, because it's hard for us to say what the density of this Epola particle, which we don't even know what it is, so it's kind of hard to assign that a density. But say my paper gives something that the scientists could actually look for. So I'm looking for this neutron C, okay? So I'm looking for experiments that would either confirm or deny that. But you'd have to specifically look for it. Like I said, neutrons are, especially ones which aren't moving. A neutron which is not moving, I would contend, is almost impossible to detect. It's the only way that we can detect a neutron, either by its decay, or if it hits something. But if it's like totally motionless, as it would be in the neutron C, it would be almost impossible to detect, not unless you had a way to just tear it apart, which is what we see in pair production or in these collision experiments. You have to find a way to tear it apart in order to give away its existence, right? Otherwise, I would say almost impossible to detect. But I would think that someone, given that hypothesis that space is filled with neutrons, could design an experiment that could conclusively say, yes, there are neutrons in space, or no, there are no neutrons in space. But like I said, there are other experiments already, like the Lamb shift, which indicates...
I think Bill Lucas already explained to you that they've done that, and the answer is no, there are no neutrons in space. Didn't he already explain that to you?
No, I didn't hear anyone exploring that hypothesis.
Didn't you explain that to him, Bill?
Yes, I'm saying that neutrons can be controlled by electromagnetic fields, because the neutron has a magnetic moment and a spin electromagnetic field associated with it. And so there's two ways you can get hold of it, and you can move it, you can accelerate it, you can do whatever you want, stir up the vacuum, and all that can be measured.
And they didn't measure a sea of neutrons, right?
They weren't looking for a sea of neutrons is the problem.
They didn't measure one. But
well, you cannot find something that you're not looking for is the problem.
They were looking for it.
No, you were looking for neutrons. That's different than looking from a surrounding sea of neutrons.
No, we can take a vacuum and we can see it should have a neutron sea in it, and we put the right fields on it, and we don't stir up the neutrons, we don't excite them, we don't do all those things because there are no neutrons there.
Well, you do see things that you put fields on. I mean, we measure things like the electrical properties, and those are properties of dipoles, right? So it's like we do measure something in the vacuum of space.
Well, my question is,
generally only be reproduced by there being a physical
hold on,
field.
Franklin. My question is, if there's a sea of neutrons, then how can you identify a neutron?
Only by its motion. It has to be in motion and has
well,
to
there
have
are neutrons supposedly in atoms, right? They're not moving.
That's right. And when they're there, that we can't really detect them, except for maybe the mass that they add to the atom.
I think Bill's explained to you that your theory and your thesis is wrong, and end of story.
And I would contend that he has not. I mean, he has only pointed out that, yeah, we can generate neutrons, absolutely. We can detect neutrons, absolutely. We can manipulate neutrons to a certain extent, absolutely. But still not had any actual experimental evidence of someone looking for the neutrons.
From everything that comes out of your mouth, Franklin, my conclusion of everything that comes out of your mouth is that you don't accept any experiments that don't agree with what you believe. So you have
I just accepted every experiment.
Hold on. You have a bunch of pre-existing ideas that you say in your mind to me, but you insist that you're right anyway, even when people say what you say doesn't make any sense. So you only believe what you say and what you believe, and what other people say you ignore and deflect and dismiss. So we're not really having a scientific discussion here. We're just talking, wasting time talking.
No, every single time you have an argument, I will have a reasoned counter argument to explain why I believe this is true. And I will explore things like I'm still interested in Dowdy's experiment where he has something where he can rotate and he can apparently recover individual components. But like I said, I kind of doubt his claim because he was talking about polarization. And any experiment which involves a radial rotation would not recover the time varying a magnetic field along the length of travel. So you would have to have experiment along the length of travel showing that you can recover this time varying magnetic field, which we should be able to do. Now that's the experiment I'm looking for.
I hate to tell you this, Franklin, but the satellite communications industry has been using antennas based on this principle that you said doesn't exist and can't be proved. And the satellite communications industry has been using antennas and doing this with radio waves for before I even graduated from college in the 1960s. So, what you're saying is just counter to the facts of what engineers know and do. And you're just insisting it's so because you say so and you don't want to believe it. It's just not, it's not worth even talking about. We're not talking about science. You're just arguing to argue.
No, I'm saying that there is a significant thing which is wrong with physics. So like that's not unusual for people in the dissident science community.
Yeah, but you've identified the wrong things. That's the
problem. This is totally the right thing. That the electromagnetic wave has been misunderstood.
That's just your opinion, and you're not convincing anybody else that opinion is correct. Bottom line, you're not convincing me. Sorry.
Well, that's okay, Harry, because you've agreed
and
that everything I say is incorrect.
Keep saying it over and over and over again. And when I try to explain to you that you don't understand and what you're saying is wrong, you deflect and refuse to accept it because you've already established in your head what is true, and you don't want to believe any facts that any other person can present. So we're not doing science. We're just talking at cross purposes.
Well, oftentimes that is what science is, especially when someone is trying to make, say, a completely radical hypothesis, which I admittedly am doing. I'm saying that 100 years of, like you said,
hypothesis doesn't have any facts behind it. None.
Like I said, show me the experiment. That's a fact.
I just explained to you about circular polarization, which you say doesn't exist, apparently, at least that's my understanding of it. And I just explained to you that satellite communication systems use that every day. It's a well-established technology in electrical engineering. And I think Ed Dowdy was trying to explain the same thing to you. And you just basically reject it. So what's the point of having a conversation when you reject facts?
I'm not rejecting facts. As I said, when I play around with these materials, quarter wave plate theoretically produces circular polarization.
What do you mean theoretically? It actually does. It works.
Yes, and I observe exactly what it does. Now the thing is that people understood how the planets work with Ptolemy, right? Now that worked perfectly well.
It's just an evasion. I think we need to close the discussion. And next week, let's actually have a science chat based on facts.
As long as the equations, this doesn't change any of the equations, known equations that engineers use to design systems. But what it does is that it just changes what's behind the curtain. Physically, what's really going on here. Now, maybe it might be some advantage that to radio if we truly understood how these things work and say what circular polarization really is, and we might be able to make more advances based on that. But
I think engineers understand what circular polarization is because they use it every day.
Yes, they totally understand what it is, and from a practical standpoint, they can use that practical knowledge and do it. Engineers really don't care what the theoretical basis for these things are.
They design all these things based on the theory of electromagnetism. I know that because I worked as an engineer for years and years and years. And I know how these things are built. I know what the theory is behind them. And you're saying that's all wrong. I'm sorry. Okay, I'm sorry. It just doesn't make any sense for somebody to say that, which is so contradictory to the world of experience that we live in. It just doesn't make sense.
But yet that is exactly what I am. What I'm exactly
and then you talk about a neutron sea, and then Bill Lucas explains to you that they've done experiments and show that it doesn't exist, and you refuse to accept that. So we're not talking about science; we're just talking about making fantasies.
No, I was pointing out that I have not seen an experiment that's looking specifically for the neutron sea. I accept everything that Bill said. That is totally true.
Well, do you accept that he's shown that you're wrong?
Well, I'm trying to convince Bill that he hasn't done the experiment to show that neutron as a static element in your experiment doesn't exist. Like I said, I'm explaining what's the difference between a neutron you can see and one you can't, is that a neutron that you can see is moving. The neutron that is not in motion, you cannot see. You have to design experiments.
People have been looking for this so-called ether for a while, and they haven't been able to find any of these neutron sea ether or any of these ether things. And so I think speculating and building a theory based on things that can't be shown to exist is sort of fruitless.
Well, there's already experiments that are consistent with that idea. Like say, Lamb's shift is consistent, pair production is consistent, annihilation experiments are all consistent.
You're not
all those
listening
experiments
at all,
are
you?
consistent.
Try
with
listening for a change.
Existing.
Try listening.
I am listening, but are you listening?
It might be said, if I may butt in just very briefly, that you have found an anomaly in the conventional explanation of things, and fair dues to you. We're all doing that, and we agree with the anomaly, and the conventional view is not quite correct. But I think you've very rapidly perhaps gone too far. You've thrown out everything. You've thrown out the baby with the bathwater, and one has to be a bit more cautious. I agree in the necessity to challenge the accepted view, but that doesn't necessarily mean that everything which flows from that is erroneous. So that's just my very brief summary of the discussion recently.
Obviously, as Harry says, that things like circular polarization, like that, is one of the hardest things to that faces, say, this hypothesis, right? And like I said, I did not know how that thing reacted, or I could possibly explain how that circular polarization works until I actually played around with these materials and just observed and measured and experimented and see what this thing does. I mean, did it do something, this weird circular spiral thing that I can't possibly explain? Or is it something as simple as just flipping the plane, the polarization plane, which is what I observed personally. It was just these quarter wave, physically what these things mean in an experiment that I can conduct is just that kind of simple thing. I didn't find anything about spiral things, but it's true what Harry says about, they use circular polarization a lot in satellite systems to recover certain kinds of signals. And certainly that's something I could look into more. So certainly I think polarization having to do with radio waves may be distinctly different from light waves, because once again, we see this dichotomy between EM waves being generated by atomic processes versus EM waves being generated by stick antennas or dipole antennas. So certainly there's more to look at that, but I would say that as a scientific philosophy, that it's okay to question even long-standing science theories. And and once again, I admit I could be completely wrong. After all, I just blasted this up this last week, and only yesterday figured out what circular polarization was. So this is all completely brand new, and only based upon a few hours of research, which is not much. Okay, but this, like I said, this is something that as dissident scientists we will often do, and since we were talking about that, I decided I would just blast up a paper and see what you guys thought. So probably no one believes me, Harry, so probably everyone's in your corner. But I just put this up as a possible explanation, which would radically show, I mean, if this were true, yeah, this would mean 100 years.
Here's my thought. What Ian said, I think, is interesting, and he sort of reflects my view. The problem is there are things that aren't really understood. Like, you're right in saying that the electromagnetic wave isn't well understood, and that may be what Ian was talking about. And I think we have disagreements on that, and I don't think the mainstream does a very good job of presenting it because their theory is incomplete. Saying that the theory is incomplete and doesn't really explain all the things that need to be explained, if we want to use that word, isn't the same thing as just tossing it out and discarding it completely. So, I think it would be better to say these are what the anomalies are that we can agree on. Okay, well, is that what we're trying to do here, or are you just saying, oh, it's all wrong and we're going to start from scratch?
It was more the from scratch thing. Like I said, that's what I said in my introduction. It's like there's a lot of evidence in favor of the current picture, right? And that there's just no possible way that I can cover all of that.
Let's go back to let's go back to the first picture that you started with. Okay. My point here is that's not something that's literally true. I mean, I don't know that anybody believes that picture is something that's literally true. It's kind of an attempt at a representation of, in a very simplistic way, to convey an aspect of the electromagnetic wave, but it doesn't tell you everything about it. Okay. And because it doesn't tell you everything about it, it's just a simplistic picture that sort of conveys a sort of vague idea of what it is, it's pretty easy to criticize, and it's pretty easy to not understand what it is. But we're talking about something that we really don't know, and our minds really can't visualize what it is very well. And to me, that's kind of what the issue is. And do you understand what I'm saying? You're picking,
yeah, I mean, that's totally the issue. I have a hard time visualizing that.
You're picking apart this representation without really appreciating what it is trying to convey. It's simplistic. It's totally simplistic.
Yes, well, as what is my usual shtick is that I try and take stuff like, that diagram, which I have, which like you said, maybe an oversimplified, even wrong kind of representation. It's like people explaining gravity by putting a bowling ball on a sheet. I mean, it has nothing to do with gravity. And maybe this picture doesn't have anything to do with really electromagnetism, but it's just something that they put up there for the science newbies to just grab a hold of. But although I think it's more than that. But that's why, as a physicalist, I always try and grab hold of things that I can.
This only shows. I mean, it shows a progression through space, but really, it's also a progression through time. And so, one of the things that people get confused about, and I see this all the time, is people are confused about time and space and velocity. And because this picture, it could be a representation in time, or it could be a representation in space. What is it?
I would say it's both.
Well, it can't be both. It's one or the other.
Well, if this was a standing wave, then that could be a physical representation.
Well, that's not really what I'm trying to get at.
But in any case, we're kind of like way over time already. So.
Well, the point is that these representations that you're talking about are basically conceptual simplifications. Think about it that way. How to understand that aspect of it.
But the whole point of this paper was to say that, it's not those things. It's something that we can understand, which is sound wave. That was the hypothesis.
I agree that it's easier to understand a sound wave than something that's more complex like this. But even so, a sound wave's pretty complicated. And drawing a picture of it, of a sine wave, doesn't really tell you the whole story about it.
Nope, but there's some hope that if it were more like an ordinary sound wave, that we could have a better understanding about, at least in our heads, how that works. But like I said, we're kind of over our time here. I thank everyone for participating, and I did send a link to this paper in the media announcement, and I'm always interested in any specific comments. So specifically, for Dowdy, if you can send me a web link to the exact experiment that you were talking about, I would be very interested in that. I mean, the only other experiments I've heard about concerning this question were people who put specific oriented antennas that would only recover part of the component, the transverse component, depending on how they oriented. And when they did that, they found out that they really couldn't recover any such components, showing that there were no transverse components. Now, I don't have the reference for that. I read that a long time ago, but that's the only experiment actually, based on the experiments to try and recover the actual electromagnetic action. But in any case, that will do it for this week's episodes. And if you guys got any other topics coming up, we're having a talk by Lori about the nature of light coming up. So watch for that experiment. That's the next person we have. And if you have any other topics you'd like to speak about, please just send me a note. Or if you have any comments about how you thought the talk went, please send those to me as well. All right, but that will do it for today.